I have achieved a breakthrough with in-context learning, a 15 times speed up and 20% accuracy gains. As you see, throughout all the iterations, our large language model using parallelized research was able to reach 72% accuracy. And in the previous example, if you see my previous video, we had reached 65% accuracy, maybe across about 7 hours, utilizing the uh, cyclic memory with strategic reflection. All of that actually exists in the parallelized research, except reaching 65%. It took about 25 minutes, and in about 7 hours, we have actually reached 62%, which is about 10 to 15% improvement over the original, the previous implementation. We can also see this script also generates a real-time HTML, which we can see on the right. This is the tree structure that were explored. The yellow ones are what was over 70%. While it's creating, it created this 1,500 solutions, predictors, and we will take a look at the data set of what it is predicting, but they look like this. The best, one of the best solutions actually looks like this at 71.2% accuracy. And look at the complexity of this. So this is probably not exactly what we want, but the fact that the model was able to hone in on the solution, quite quite interesting. So this system utilizes all the previous advancements we have made to facilitate in-context learning to solve unseen difficult math problems in this case. And on top of it, we have implemented tree search, which sped it up dramatically, as you've seen, and increased the accuracy as well by funneling the model's efforts towards more promising situations and scenarios. So all the code files for this, like all the previous ones, will be available in my Patreon if you're interested. Take a look. As a paying member, you will also have access to over 400 applications powered by large language models, as well as exclusive videos and weekly meetings. And I offer consulting membership tiers as well. Take a look if you're interested. So our complex data set consists of 10,000 rows of five variables, A, B, C, D, and E, and an output category from 1 to 4. Just to, if you remember, our original attempts showed flat progress, so we did not see in-context learning in those cases. But the fact that they reached 45 to 50% accuracy, even in those cases, were remarkable, because by random chance, you would only expect to achieve about 25%. So the model actually had figured out something beyond random chance. So that already is in itself remarkable. And I'll tell you why. The underlying function here is not that complex, but it is sufficiently complex. That's not the point. The point is that the possible configurations of interactions, even just using regular arithmetic between five variables, each one of them ranging from 1 to 100, is just enormous. The fact that the model, even with a rudimentary approach, which did not display in context learning, was able to achieve 47% from our previous videos, was remarkable. But so the first hints of in context learning with the last video, reaching about 65%, was all that much more exciting. And now that we were able to achieve the same level of performance very quickly and even surpass it, reaching 72% is just remarkable. And the reason why it is so is that, so we have five variables, A, B, C, D, and E. Each one of these variables is a random number between 1 and 100. And our final output is a category of from 1 to 4. Right? So essentially, there is a mathematical relationship between these five numbers, which leads to their categorization. So it could be something like this. Let's just take two numbers, okay? Let's just say A is 2 and B is 3. So Just from these two numbers, there can be so many different mathematical relationships which lead to their bucketing or categorization. For example, we can say, well, we're going to multiply these and check if they are below 7. Then, if that is so, we're going to assign to 1. If otherwise, then we're going to assign it to, if it's larger than 7, then we're going to assign it to 2. Okay, but we can also say, well, we're going to multiply A with B like twice, right? And then check to see if it's over 15 or over 150. So there could be quite a lot of possibilities just with two numbers. And these numbers can also vary between 1 and 100. So there is astronomical amount of variety that can exist between five numbers, even just utilizing addition, multiplication, subtraction, and division. We could have also said 2 minus 3. If it is a positive number, then assign it to 3, for example. Otherwise, 4. So the fact that the model actually figures out anything at all about this is just remarkable. Now, we could solve this data set beyond 95% efficiency using traditional machine learning algorithms like random forest or especially XGBoost, for example. But the thing is that those are black box approaches, and we will have no idea what the underlying mathematical relationship was. Here, in this case, we actually get actual results, which we can see, which actually gives us a hint of what the underlying mechanism might be. Now, the original function was maybe something a little bit larger, nothing like this, but like maybe something like this, right? However, the really high scoring uh, predictors that it was created, like this one is a good one because it's at 71.2%. Now this is really complex. This is far from the original function. So it gives us an idea of what the original function might have looked like. So that's good, but this is way too complex. So you can look at it and say that that is insane that the model actually is able to keep this in mind and actually improve it iteration over iteration is impressive. It is, but there are also ways like I'm exploring JEPA, which is a generic Pareto style implementation, which I already have, but it did not show improvement over tree search. And I'm also working on a generalizable system, which takes in and tries to solve any user query. I will be making separate videos on those. But this tree search showed great promise, and we did keep the cyclic nature of it. So if we take a look at its README real quick, so this is a system that uses parallel Monte Carlo tree search to automatically generate and optimize Python predictor functions. Now we employ parallelization of the tree search by exploring 5 different branches and 4 children of each branch. Now this is entirely customizable with the parameters. We are using the new Sonoma Sky Alpha model. I really like this model. It's actually very smart, and also it's free and it's fast. Now, let's take a look at this README. So we also include hybridization, which is every 50 nodes combine the best performing functions to create hybrids. Stagnation detection, when the accuracies get stuck, we force a perturbed creative variation inducement. Periodic reflection. So this was what actually made the biggest difference, right, from our previous example projects. So every 3 nodes, we analyze the progress and adjust strategy. We can take a look at what this looks like at the end. So these are all the reflections that this system went through. So it actually analyzes the current progress, gives a strategic analysis, and then proposes new strategies going forward. So this actually is a very crucial step, reflection step. And other important things was the cyclic learning, right? Because in our prior attempts where we flatlined actually and did not see in context learning improvements was where we were trying to craft. We were treating each call to the LLM as a new call. So we weren't maintaining message history, but we were trying to craft perfect prompts. I think there is still merit to that approach, which I will try to explore more. But in this case, we are keeping a message history so that the model can learn from its experience. But then we employ a cyclic learning where we reset the message, history and actually include experiences that the model has had, such as best performing functions, where the best performing predictors has failed, and also the reflection, and then we let it continue. In this case, the reflection, the cycle is set to 10, uh, 10, I believe it's set to 10 nodes. So here are the hyperparameters of this. We can use both OpenRouter or OpenAI. We are using Sonoma Sky Alpha, but feel free to use any any model. We set it to total 1,000 nodes for the uh, stop after reaching 1,000 nodes. That it'll stop. We show 10 mistakes that were made by the predictor that was generated in that iteration. You can set the predictions folder and the plot name because we are updating the plot in real time. Also, this 3 visualization HTML is generated in real time. We can actually run this while we are talking about the hyperparameters or the parameters, and then we can see this visualization being drawn. As you can see, it is parallelized, so we are exploring 5 branches at the same time. If you look at the code, here is the we yeah 3 children per expansion, 4. That's parallelized. Also, parallel branches 5. That's also parallel. And as you're running this script, if you download it from my Patreon, you will see these predictors being created and tested and deleted over time. And eventually, the folder and the plot will appear here once we complete node 1. Okay, let's come back. So top performance to keep. So how many number of top performers to preserve between cycles? Examples per performer. So we do keep these top performers, but these top performers fail in some of the rows in the data set. So we collect those examples, the failure examples, and present them so that the model can have an idea of where the best performance went wrong. See this PUCT. This PUCT is a acronym for Predicted Upper Confidence Bounds for Monte Carlo tree search, and that determines the exploitation uh, frequency. The higher this number, the model will be more randomly exploring different parts of the tree. Here are HTM3 visualization just here. We can keep track of it here. Also, our new plot has also appeared. From this plot, we see that we are currently at node 1, indicated by the star, and all the children, as they come in, we are actually seeing their results. So in node 1, we explored 5 branches and 4 children each. So that's why we are seeing 20 accuracy numbers each, and it is also reflected here on the HTML view. So these are going to actually update automatically. So if you set a high PUCT value, then you will explore more randomly. And if you have a lower PUCT value, then you will explore more of the more promising paths, such as high accuracy results. Children per expansion. 4, hybridization frequency. Every n nodes try to combine the best predictors. Stagnation. Every 10 nodes, check if stagnation has occurred, meaning that we are plateauing. Try to perturb the system to become more creative. This is HTML visualization frequency. Every 1 node, we update reflection frequency. Every 3 nodes, we write these reflections, as we have seen, and pass it on forward. And also how many of them we are going to keep, which is reflections to keep right here. How many top performers to keep, failure examples, how many reflections to keep, reflection frequency, and how many parallel branches. And also, here are the just in case API calls fail, we do some retries. So it's really interesting. There's quite a lot going on here. It's 1,400 lines, and we do create the HTML dynamically from this file itself. Yeah, so I will be exploring more. I have also built, as you can see, the RHTML has updated. 5 new branches were explored with 4 children each. So It's a really interesting system. And if you take a look at our uh, plot, we can see that we've already surpassed 55%. In the second node, we are on the second node as indicated by the star. So the README is very detailed. You can read all about it. So the tree search is an interesting algorithm, but I think it serves mostly for speeding up the search process because of the parallelization of it. But it also guides the model towards more promising paths from exploitation strategy. So it is less random. But the thing that here makes the biggest difference is the cyclic approach coupled with periodic reflection. I am exploring JEPA as well. Just to show you this idea, the tree search idea was implemented from this Google paper. AI system scientists write expert level empirical software. They use tree search. I was inspired by this and used some of the same methodology. Also, there is the JEPA paper. Reflective prompt evolution can outperform reinforcement learning. I have implemented about 85% of this paper combined with research, but it did not outperform research. I will be making a separate video on this. And I have also written a separate script, a project, which generalizes this to almost any question, without which may not have a perfect solution. Here, in this case, each one of these mathematical problems have a solution, right? It comes in form of a categorical value of 1 to 4. Another thing to note is that the tree is also updated in the terminal. It's pretty fun. Yeah, so I will be sharing more information on the JEPA variation and also the generalizable variation. So I'm going to stop this terminal right now, and I will be uploading this to my Patreon. If you're interested, please consider becoming a paying member. Like I said, I have hundreds of projects there, exclusive videos, weekly meetups, and I also offer consulting if you need any help, want to learn something in particular, or just want to get in touch with me. There are membership tiers for that. You can find all the information at Patreon. And depending on where you're watching this from, the link to this code base will be in the description or in the comment. Thank you for watching and see you in the next video.